Started. Okay, so share screen. So let's start. So who wants to start? So here is the instance given. I'll just zoom in a little bit. So who would like to find a man optimal matching here? Anyone?
I can do.
Just one moment.
So one is the easiest: M1W1, M2W2, M3W3.
Okay, so the man optimal is easy. So there are three of you. I think Arvind left, right? Right, just a few minutes ago. I think he will rejoin. So man optimal matching is say M0. So I'll try to be consistent with the notation here in here also. So it is M1. M1 is equal to M1 W1 into W2 so maybe Shubham can start. You can try to find the rotations that are exposed in this particular matching. So let's call it row 1. Since it is not a Neumann optimal matching, that means there exists at least one rotation. So you can start.
Yes. So for the so M1W2 will, I think.
So what are the couples in the rotation? M1?
Yes, I think M1W2.
W2?
Okay, no, I mean M1W1.
Yeah.
Where W2 prefers M1 over W2.
Yeah.
And
so I'll draw it after that, and then
below that there is W3. Then M3W3 is also, then M2W2 is also there.
Yeah.
Because in the list of, wait. Yes, so M2W3 is there. Then M3W3, because W3 prefers M2 to her current partner M3.
Okay, so let's draw it. Okay.
Yes.
So there is okay, maybe I should not use red. Okay. So there is M1, and there is W1. Okay, and
yes.
In the preference list of M1, we can see that
W2
M1,
is below.
W3 is below W1, but if in the preference list of W1 prefers M3 over M1. Okay, let's draw the current matching. Okay, so this is the
yes.
current matching that we have, so it will be easier. And
yes,
for M1, it is this. Please tell me if there is some mistake. Okay, so this is the current matching, and in for M1, W3 is below W1, but we can see that M1 is
below, so that is not there. But W2 is there, and in the list of W2, M1 is higher. So M2 W2.
So here is W2. Okay, so and now we can see that in the preference list of W2 is currently matched with M2.
M2, but M1 is higher. So that's a
And-
SM pair.
So M1 is higher, and that means we have a sorry, in the preference field of W2, you can see that W1 is there, and in the preference system W1,
M2 is higher.
M2 is higher. So we
So this
can
is a
go.
small.
Yeah, so this completes the cycle. And in this cycle, we can see that M1 prefers W1 to W2, W2 prefers M1 to M2, and M2 prefers W2 to W1, and W1 prefers M2 to, sorry, M2 to M1. Okay.
So, but we
So-
could have gone. So we could have gone forward and found a bigger one also, like M3W. Not needed, but I'm just saying, like M3W3 also can be extended.
How?
Like M2W3 is also there, because if you look at the list of M2, W3 is lower after W2, but if you look at the list of W3, M2 is higher. So
But the problem is in the list of M2, W3 is not the first force that is worse than W2, which who prefers W2 over her current partner. W1 is before that, right? So we cannot go to W3.
Oh,
So
it
what
has to
was
be the first one. right? It has to
yes,
be-
yes. Sorry. It has to be the first one.
Yeah, no worries. So what was the definition? If we go back to definition, so SMM was the first woman in the M's preference list who after M of M, after his current partner, who prefers M over her current partner. That is the SMM. So here we are assuming that MI, WI are all in the matching, and WI plus 1 are the SM of MI. Here the rotation is correct, but the problem is that W3 is not the SM of M2, right? That is W1. W1 is the first
Is
one
also there.
after W2, who prefers M2 over her current
Our
partner,
current
that is
partner
M1.
M1.
Yeah,
Yes,
so that's why we
yes.
cannot go to W. So that's why
Right.
we can't say that rotation containing M2 W3 is exposed right now. Okay, so this is the one. This is one of the rotation. Is there any other rotation? So if we can just go from M3, so M1 and M2 are covered. So let's start from M3. Okay, from M3, let's we have M3 to W3. We can go right, and in the preference list of W3, sorry. And the next one is W1. So in the preference list of W1, we can see that
Yeah.
No, M4 is not even there.
Yeah, sorry. No. In the preference list of M3, W1 is after W3. And in the preference list of W1, if I go there, so we can see that in W1 prefers M3 over M1, her current partner. So it is W1, but we'll see that we'll have some problem here actually. So here we can see that from W1 we'll come to M1, and now you can see that you will have this particular cycle over here, right? From M1 you will go to W2, from W2 you will come to M2, and from M2 you will
but this
come
will go to W1. Yeah.
Yeah, so
Right.
this will be excluded.
Useless.
So this is the same thing we are getting. And similarly, I think if you try from M4, you will have the same problem. Or do you want to check, or maybe
Can you check for M4?
Yeah, I'll check it. So shall we keep this picture? I just started to erasing. So I think if this picture is we can check it. And if we check from W4, what someone can help me here? Tell me. So from M4 we are going to W4, right?
W4. Yeah.
And from
If you go to
W4,
M4's list.
no, we will go to
Next one is
W2's
W2.
list.
Yeah.
We'll go
So
to W2's list.
W2.
W2 doesn't prefer M4 over her current partner. So we go to W3. And in the W3's list, W3 prefers
M4 of the current partner.
M4 over current partner.
So W3 is the one which will go with M4.
Now, can you see what is happening here?
W3 is matched to M3.
You will have
Yeah,
can
you'll
you
have
see
the
that?
same diagram again, and again it will
Yeah.
end at W1.
Yeah, so basically you will have this picture over here, right? And that's why, I mean, and eventually if you check from W5 also, you will have the same situation, and you will have this only this. So actually in the example, this is the only rotation that is currently exposed. Okay, so if we apply this rotation, so what will be the current matching? If we eliminate this rotation, what will be the matching? Anyone can tell me?
So M1 will, can you just scroll a bit up so I can look at the cycle? Look. So
Yeah.
new matching would be M1 W2.
I'll use the blue color then. M1 W2
And M2 W1.
M2 W1, and the rest will be the same, right?
Yeah. Yeah.
Yes.
And we will basically remove these vertices. Remove these edges. Basically, removing this from preference list means we have removed the edge W1 M1 and W2 M2, right? So in what will be here? So in W1 it will be M2, and in W2 it will be M1. I think it is correct.
Yes. Yeah.
Okay. Now, can anyone tell me what is the the second preference list, second rotation, the next rotation? Maybe someone else. I think Shubham, you said the first one, right?
Yes.
Okay. So maybe Tejas, you can
Okay.
try.
So there's no point starting with M1. So let's start with M2.
Why? Oh, okay. Yeah.
Because
Of course.
M1 has nothing below the current partner.
Of course.
Yeah. So we start with M2, and we, after W1 is W3. So let's look at W3.
Yeah.
On the preference list of W3, M2 is higher than W3's current partner.
Maybe I should write it down, right? Somewhere. Just one moment. It's not. Okay, it's not working here also. Okay, so I think I cannot copy the page to the next page, right? Or can I? Just one moment. I'll check if I can copy the page. Control D. Control V. No, I cannot copy it. Just one moment. The page I print screened. I'll just print screen it one more time, and I'll just paste it there. Okay, so it will be faster. This is the example. Print screen. Control A, Control V. Just one moment.
Yeah.
Control X. Okay. So if I go to lecture note, Control V. I think it's visible now.
Yes.
Control D. I'll just paste it 2 more times because there will be like some other rotations also. Okay. So okay, for now this is fine, I guess.
M2 was matched with W2.
Yeah, so maybe you can tell
this-
me what is the matching currently. M1 is matched with W2.
W2, yeah. M2 with
M2.
W1, I think so.
Yeah, and rest of them are the same.
3, 4, 5. Yeah. And
Just-
W1 is with,
W1 is
with
M2 and M2 is with W1. This is it. And this is not there anymore. This is not there
yeah,
anymore.
that's fine.
This is not there, and this is not there. Okay, now you can
Yeah.
tell
So
me.
now
what
we
is the
start
reason.
with, we start with M2 and we check if W3 is valid. So W3, if you look at W3,
M2 is the first is M2 is the partner of W1. It's there.
yes, correct.
And now we check W3.
Yeah.
And
so W3 prefers M2 over W3's current partner. So that would be your thing. M2 with W3.
yep.
Then W3 is matched with M3.
Yep.
So now we look at W1. On the list of W1, there's nothing. So W1 can't be. So look at W2 now.
Wait. In the preference list of M3, there is W1. in the
So,
preference of W1,
W1, yeah.
W1 prefers
Yeah,
M3
yes,
over
yeah,
F2.
yeah. W1 prefers M3 over her current part. So that makes sense. Yeah. Right.
Yes.
And maybe, I mean, yeah, I'm not doing it right now. You can check. This is the only rotation again. Okay. I mean, you can try at home, I guess. You can do it. I'm just stopping here because of the time. Otherwise, this will be the only rotation. Oh.
Sir, why have you erased, like in the list of W2, for example, why have you erased M2?
Because when we eliminate them, we basically remove those edges.
So, but cannot it be useful again?
No.
No. Okay.
Because
Okay.
I mean, it cannot be useful because so basically what we will do, we will first find all the rotations that are exposed currently in that graph. Okay, and after that we will remove all of them one by one, and only the rotations that are exposed currently, they can use these edges, right? Okay, one more. Yeah, it will not make a problem because for any two rotations we have checked that they can be either disjoint or they can be identical. Okay, no
yeah.
two rotation can have a common edge.
Yes.
That is the reason. Okay, so here okay, so this is the rotation. Now can anyone tell me Tejas, you can tell me the current matching that we'll get, the new matching?
Yeah, okay. So in the new matching, M1 will stay the same. M2
Yeah.
will go with W3 and M3 will go with W1.
And we'll remove them.
And W1 goes with M3 now.
W1 goes to M3 and we remove it, and W3 goes to
W3 goes to M2. Yeah.
W3 goes to M2 and we remove it also. Okay.
Yeah.
And the rest of them are the same. Okay. So
Hey, can you repeat one more time why the Subham asked that why should you eliminate? Can you repeat the reason once more?
Yeah, because any two rotation cannot share any edge. Because in this example also you can see that where is the example? So did I remove that? Okay, sorry, it came after that, so I have to rearrange it. Okay, so in this example also we can see that when two rotations share an edge, they basically, I mean, if you take one edge, they basically dictate the whole rotation, right?
Okay, yes, correct.
So that's why, I mean, no two rotations can share an edge.
Yeah. Okay, so I got that part, but then okay, and hence edge cannot be reused because because if it was used once, then it will not be used in a different rotation afterward.
Yes.
Is that
yes.
But like I mean, okay, so my question is, for a fixed matching, it is the case that no two rotations share edges, but here after we change the matching by one rotation, then what we get is now a different matching. And then for that, so like a rotation in the new matching and rotation in the old matching, they can have a common edge, right? Because the matching is different.
No, actually what will happen is that so if they have a common edge, suppose M1 has like W, suppose let's go here, M1 has like a W1 and the W2 and then W3. Okay. And M1 is currently matched to W1 and W2 is his second best choice, right? And we are always removing the edge that is like currently matched. So if it is present there, this is not removed at that time.
Yeah.
So I mean, there is no until this edge is there. There is no point of making a rotation with W1 and W3. I mean, there can exist something like that M1 is there and W1 is there and W3 is there also, that W3 prefers M1 over her current partner. But in that case, the point that W3 is the second best choice of M1 will not be valid.
Because W2 is the next one.
Yes. Okay.
Okay.
So that is the reason we have to eliminate W1, because if it is valid with W3, then it will also be valid with W2 also. I mean, sorry, if it is valid with W1, that M1 prefers W1 and W3 prefers M1 over her current partner. But then it will also be valid for W2 when we remove W1. Like M1 is currently matched with W2 and W3 is there, and W3 prefers M1 over her current partner, and everything is so.
Yes. So basically, can we say that one edge determines the entire rotation?
Exactly. One edge basically determines the whole rotation, and W1 and there won't be any rotation containing W1 and W3 because there is one W2 in between them who basically blocks it. I mean, no, not blocks it. Block will be a bad word. Who basically doesn't allow us to. Allow us to have this rotation, because if W2 is present, then W3 M1 W3 cannot be the best host who prefers M1 over her current partner.
So is that why we have put the second best in the definition of rotation?
Yes.
Yeah.
Otherwise, the proof will be complicated. I mean, there can be this kind of rotation also, that M1 W3 will also be present there.
Yeah. Yes.
Sorry, where is second? I mean, we just said that the woman after the current partner who is blah blah blah. So we didn't say second best, right?
No. But I think by second best he meant like okay, the second best is not a good word. The women after the current partner.
Just after the
and not the second one.
Yes.
If we choose the second one, then we'll have this kind of rotation also.
I mean, W3 would be the second one, but W2 is the first one.
Yeah, I meant the first possible women prefers M1.
First possible,
yeah. Because one thing you can see that if you take a symmetric difference of the man optimal matching and the women optimal matching, then also you will get some rotations, and those alternating cycles, but those alternating cycles may not be rotations. I mean, I will see. I mean, after I complete this example, we will just take the symmetric difference between the man optimal and the women optimal, and we will see that it is not a rotation because they are alternating cycles, but they don't satisfy the condition of rotations.
So you mean that we can use them also to jump between two matchings, but we will not. But we will be jumping between several matchings. Like we'll be skipping if we apply them.
Exactly. And this will not give us the structure. I mean, we can always take some alternating cycles. I mean, if you take the symmetric difference between man optimal and the women optimal and apply those cycles in the man optimal, then also you will get the women optimal directly, but that will not give you the structure of the whole structure. So this has a property that this will basically give us all the stable matches.
Right.
Okay.
And can we also say that when we are applying a rotation, then we are going down in the partial order of matchings? So can we use that, for example, here to in the list of W2, after we have exposed and eliminated the first rotation, then can we not remove M3 and M4 also? So scratch them out, because we know that we will never be using it again.
Yeah. Okay, so remind me, there is an extended Gale-Shapley algorithm that I will teach you maybe after this rotation thing. Okay, that will clear your idea. I mean, this is a good point actually. So this I'll tell you about this extended Gale-Shapley algorithm. Okay.
Okay.
Okay, great. Just one moment. I'll just stop the mobile. Otherwise, it will just give me notation in the laptop. Yeah, now it's fine. Okay, so we have this. Now we have the second matching. So where were we? Okay, I have to change these pages because it came before. Okay, so now we have this, and this is the current matching. Shall we go to the next page? I guess. So M1 is W2 here. M2 is matched with W3. Then. So what will be the next rotation? Can anyone tell me now? Or so who wants to tell?
Yeah, I can tell.
Just one moment. First, let me fix this. M3 is here, and
M2 W3.
M2 W3 is M2. So this is the correct one, right? And we have removed. Okay, so everything after that we don't care, and everything on this side we care. Okay, so from here, what will be the who is presenting now?
Shagnik.
Yeah, please.
Yeah, so M2 is matched with W3.
Yeah.
And the next woman after W3 is W5.
M2 is W3, W5, yeah.
And W5 prefers. Wait, maybe I
W5 prefers.
W5 prefers M3.
W5 will not work.
W5 prefers M5, right, over M2. Who is the current partner of W5?
Yeah, it won't work. Sorry.
Yeah.
So
why? Because W5 is current partner is M5, and M2 is the partner. M2 comes after W5. Sorry, M5.
right.
So that's why it will not work. So now I'll check the next partner of M2.
That is
W4.
W4.
Yeah.
W4 prefers M2.
Yep.
And
Over. No, think it in this way. When you are in M2, you check W4. Okay. Now come to W4 and see who is her current partner. That is M4. Now you check that if W4 prefers M2 or M4, and you see that W4 prefers M2. That's why you can write. I mean, W4 prefers M2 over M4. That's why you can write W4 over here.
W4.
Yeah, maybe you can tell me the next one, then it will be clearer, I think. So from W4, the partner is M4. Now you can tell me the next one. Yeah. Yeah.
So W3 prefers M4 over her current partner.
W4. Okay. So,
W3 prefers M4 over her current partner.
So have you checked W2? So W2 doesn't.
Oh, so now I have to check. Okay.
You have to check serially. So
right.
First you have to check with W2.
But W2 has already got the best partner.
Yeah, so she doesn't prefer M4. Yeah, M4 over her current partner. So now you can come to W3.
Right.
And W3
Cycle
prefers.
will complete.
Yeah, and this is like a minus plus minus plus minus. Oh, this is the opposite way. Minus plus. Okay, now applying this alternating cycle, what is the new matching you get, Shagnik?
So now M2 is matched with W4.
M2 is matched with W4. M2 is here, W4. So maybe different color again.
And M4 is matched with W3.
And the rest of them are fine. Rest of them are same. So if I come here, so W4 is matched with M2. And W3 is matched with M4. Okay. So now
I think there are no more rotations.
Is there? Let me. No, there is some more. There is one more. So is there any more rotation here in this particular graph? Actually, there is one more. So Aranya, you want to say? Tell me. Hello. So anyone can tell me what is the other rotation here?
Yeah, it's
Maybe we can start
M3.
with M5 and see what happens.
No, M3.
M3, okay. Let's start with M3 then.
M3 is matched with
M3
W1.
W.
M3 may match with W1, then
So W2 won't work, so we consider W5.
W2 won't work because we consider W5.
Now
W5.
W5 is matched with M5.
Mhm.
And in M5's list, W4 won't work, so it goes back to W1.
No. You say that this way. In W5's list, W5 is matched with M5 and M3 is better
M5,
than
yeah.
M3 is better than that.
Yeah,
So that's why M3 W5 edge is added, and
Right.
W5 is currently matched with M5. And now in
Yeah.
the preference list of M5, we can see that it is the next one is W4. But in
W4
W4
doesn't work.
yeah, and in W1,
Yeah, that works.
yeah, because W1 prefers M5 over M3. That's why we have an edge to W1. And now we have a cycle. So here we can see that we have two disjoint cycles from a given instance. And if we apply this rotation, what matching do we get? We get this. So by green, we have this and this matched. And here we have M5 gets matched with W1 and M3 gets matched with W5. Okay, so this is the men optimal and the women optimal matching. So we can see that we have come to the every woman prefers her best partner. Now if you check, you can find any more rotation. That's why this is the final rotation. So what are the rotations here? Okay, I'll stop the meeting and start again. Sorry. Okay. So now we can, so these are the 4 rotations. Now we can see that until row 1 is not eliminated, we cannot, the row 2 is not exposed because in this graph, only row 1 was exposed. So if we write it as row 1, so row 2 was not exposed in this graph. So it means that row 2 was not exposed until row 1 is eliminated. And similarly, we can see that row 3 and row 4 are not exposed until row 2 is eliminated. So this is row 2. So row 2 here is M2W1, M3W3. Okay. And finally, we can see that row 3 and row 4 are exposed together. So that means it will be like this. Okay, so this is the rotation poset. So is the rotation poset clear? How we are computing it?
So to find, so we got row 3 and row 4 are exposed together, which means after we applied row 1 and row 2 in order, we could have had sort of 2 disjoint cycles, the row 3 and row 4, or that would not have happened.
Yeah, so basically what is happening here, first we have the main optimal matching, and there only row 1 is exposed, and we eliminate row 1, and then we get row 2 is exposed only. We eliminate row 2, and we see that row 3 and row 4 both are exposed now. So we can, so basically there are how many stable matchings are there? So there is like M1, which is the main optimal. There is M2, which is the
After applying row 1.
Applying , and which there is M3, which is the main optimal. There is M2, which is the main optimal. There is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and which there is M2, which is the applying row 1, and which there is M3, which is the applying row 1, and on M we apply row 1 and row 2, and there is this M4. So anyone can tell me what is what can be M4?
You can add row 3. So row 1, row 2, row 3.
And what is the M5?
M5 will be M slash row 1, row 2, row 4.
And what is the M6?
M6 is where you apply all the 4. So M slash row 1, row 2, row 3, row 4.
So as I said before, rotation is basically, there is a bijection between every closed subset of this rotation force set and the stable matchings. So here you can see that what are the closed subsets? First is empty closed subset. Then the first one is, I'll just color it. The first one is this. The second one is this. Third one is this. Fourth one is this. And the fifth one is this. And the sixth one was the empty one. So that means these are the closed subsets, right? And for each closed subset, you have a stable matching. Okay, so I'll just stop share for a second, and I will share my full screen.
So what was that M? Sorry, sir. What is that M? M should be M1.
Oh, sorry,
Is it-
M1. Yeah.
Okay.
Yeah, sorry. Correct. M
And the
is
meaning of
the
closed is closed up, right?
closed up.
Closed up.
So
okay,
here-
yeah, okay.
So here you can see that this particular graph has like 6 closed subsets, as I shown in the blue circles. Okay, now if you check it here, not this one, I think just one moment. Can you see my PDF file now, Acrobat Reader?
Yes.
Okay.
Yes.
So here, if you check it, you have 6 stable matchings. And if you verify at home, you will see that if you apply one of the rotations, you will get these matchings. Okay. And on these 6 stable matchings, you can get a lattice structure, and that lattice structure will look like this. This is the lattice structure. Can you see? Is it visible, the structure?
Yes.
Okay,
Yes.
so you can try to check at home that you are getting the same lattice structure of the stable matchings. And if you just solve the whole problem once by yourself, then you will see that it will be more clearer to you. Okay. So this is basically the basic idea of rotation. So you start with so if I repeat it once, you start with the main optimal matching. Then you find all the exposed rotation at that time. And those rotations, if you apply one of them, then you will get a new matching. And if you apply all of them, then when you apply rotation, you will see that one or more rotations will get exposed. And if you apply any one of them, then you will see some new rotations get exposed. And in this way, you continue until you reach the women optimal matching, and then you will see there will not be any more rotation. And after you find all the rotations, you can build a partial order like this. So partial order, I'll just draw it here, the small picture one more time. Partial order like this, where it means that there is a bijection between the set of all stable matchings and all the closed subsets of this partial order of the rotations. And how do we build this partial order? We start with the rotations that we have exposed at the beginning in the main optimal matching. They will be on the top. Like here, it is only row 1. And after that, we see what rotations are exposed when we eliminate row 1 here. And we will see that row 2 is exposed. And after that, we see what rotations are exposed when we eliminate row 2. And we see that row 3 and row 4 are exposed. That's why there is an edge from row 3 to row 3 and row 4 to row 2. So this is row 1, row 2, this is row 3 and row 4. So this is the basic idea of rotation. Okay, so any question about rotation? So then after that, we will move to the new topic.
Sir, so can we say that this matching is corresponding to closed sets of rotations, because by the very definition of rotation and the definition of exposed, it is like that. Like everything above has to be exposed before
Yes.
something is exposed. So that's why basically closed set is corresponding to matching.
Matching, and also every matching corresponds to a closed set or closed subset.
Yes. Okay.
Yes, so it is both way around. So that's why that's why the size of the closed set. So that's why there is a bijection basically. So if you have a matching, stable matching, which is not man-optimal or man-optimal, maybe it doesn't matter. Then there is a closed subset here, and if there is a closed subset here, then there is a stable matching on the other side. Okay.
Yes.
So this is the main idea. So maybe I'll try to give you one more example, different example. So you can try to, I mean, for everyone, you can try to solve it and find all the rotations and all the stable matchings. So I hope it, then you can, it will be a good practice for you. So
Yes.
is this fine?
Yes.
Okay, great. So I'll send you, I'll find one more example, good example, and I'll send you. Okay. So the next one. So we have found this rotations, and also one more thing that we have found is we have found this man optimal matching and the women optimal matching, right? But the problem is the man optimal matching that benefits the men most, but those matchings are not good for women. But on the other side, the women for the women optimal matching, they benefit the women most, but the men there doesn't benefit at all. I mean, those matchings are worst. In those matchings, each man get their worst partner. So what is the natural so what is the natural thing that we can do from here? We can try to find some matchings that are not men optimal or women optimal. That means those matchings benefit both men and women in a similar way. Okay. So in that sense, we have some matching problem. We have some stable matchings that we are going to define now. So the first one is called egalitarian stable matching. Is the spelling correct? Egalitarian? I think I'll just check the spelling of it. Yeah, the spelling is correct. Okay. So what is the egalitarian stable matching? Egalitarian means that everyone deserves the equal right. So basically, this is the literal meaning. So here, what we say that suppose MR of MW. So suppose we are given a we are not given a stability. So MR of MW is basically suppose the rank of W in M's list, and MR of WM okay. So MR of MW is basically sorry, just one moment, the notations are not okay. So the WR of MW. So MR of MW is basically the rank of W in M's list, and WR of MW is basically rank of M in W's list, the opposite thing. Okay, so one thing is clear that M will be happier, M is happier if MR value is smaller. And W is happier if WR value is smaller. Okay, so in this sense, we can say that for a given matching, let's M be a stable matching. Then we compute this expression for this matching, that is sum of okay. So the WM is basically sum of all the MR values of MW who belongs to the matching, and the WR value of those MW edges who belongs to the matching. Okay, and our goal is to is this clear? So basically, here MR is the value. MR is basically the rank of W in the M's list, and WR is basically the rank of M in the W's list. And for if we take a stable matching, for each edge that is in the matching, we compute, we find the MR value of that edge and the WR value of that edge, and then we take the sum of all these MR and WR values of each edge in the matching. And our goal is basically to find a stable matching that minimizes this MR value, minimize this W value of that matching, and that matching is the, we call that matching as a egalitarian matching. So is the definition clear?
Yes.
Okay, so this is the first one. The next one we have, it's called the minimum regret stable matching. So okay, so for this matching, there is an algorithm of this problem can be solved in polynomial time. In polytime. Time and so there is an order M square algorithm by, I think, Arvin. So for this to find egalitarian stable matching, so this is this problem can be solved in polynomial time. Okay, so the next one is, it is called minimum regret stable matching. Okay, so what is this? Here we say that suppose the regret of M is basically, suppose MR of suppose M is a matching given. Okay, so regret of M is basically the rank of his current partner in the matching, rank of the partner of small m in the matching capital M. And suppose regret of W is basically the rank of rank of the partner of W in the preference list of W. Okay, so now what is the regret of a matching? Max of for each M and W, we compute the regret and we find the max of that, and that is the maximum regret of a matching. And our goal is to minimize regret of M. Okay. So what is a minimum regret matching? So basically what is happening here, we start with suppose we start with a stable matching, and in that matching we see the for each man we see the rank of his partner, and that we define it as the regret of that man. So if the rank of a partner is like rank of the partner of M is like suppose 5, then the regret of that man is 5. Okay, regret value. And we compute this regret value for each of them, each men and women. And then while compute of regret of the whole matching, that is basically the max of regret of each men and women. Okay, and our basically goal is to minimize that regret value of the matching. Basically we want to find a stable matching whose regret value is minimum. So what is happening here is we want to find a stable matching that minimizes the regret of, that makes most of them, almost everyone, not almost everyone. In this matching, basically, no man or woman is getting too sad. Okay, so we basically want to find a matching that doesn't make any man or woman very sad. That is the goal of this particular matching. So this is called a minimum regret stable matching. And
sir, is it the same as one where summation is replaced by max? Or,
yes.
No.
Yeah, summation is replaced by max. Yes.
Okay.
So I'll show you some examples in a moment. So there is a polynomial time algorithm. Order. So this is basically faster one than the previous one. This one runs in order M time, and the previous one had a running time of order M square. Okay. So is my PDF file visible, or only you can see the journal file?
PDF is visible.
Okay, so let's look at an egalitarian stable matching. So if you check this stable matching, this instance, I'll just increase the value a little bit. Okay, so in this matching, we can see that there are n men and n women. Okay, and suppose the underlined matching is the man optimal matching, and there is another matching that is given by the star. Okay, so here we can see what is the value of what is the egalitarian value of the underlined matching. Can anyone tell me?
N is it N?
It is
Sorry.
n plus. No,
oh,
no,
sorry.
No.
N plus n squared, because all
Exactly.
the women have rank N.
Exactly. So it is n plus n squared. Okay. And what is the value for?
Why is it n plus n square?
Because okay. So here we are assuming something. So there are n men and n women, and here, since there is no dot after M1, so we are assuming that M1 and M2 and Mn are the last choice of each WIs. Mi is the last choice of each WI. Okay. So in that way, the size of the preference list here is of n.
Okay. So the underlined thing is the actual matching.
Underline thing is one matching, and the starred is the another matching. So basically, I want to compute what is the egalitarian value of the underlined matching and what is the egalitarian value of the starred matching. That's
Yeah. Then
goal.
it is n square plus n for the underlined. Yes.
Yeah, and what is for the starred matching?
3n.
Yeah.
3n.
So here you can see that the egalitarian value can be like much lower than. So in this way, basically you can So between these two matchings, you can see that the start matching is basically much more egalitarian than the first one, the underlined one. So in this way, basically you compute the egalitarian value of a matching, and after you compute it, basically our goal is to find a matching which has the minimum egalitarian value. So here I think you can see that the start matching has the minimum egalitarian value. I'm not going with the algorithm now because that is much more complicated, but you can see that the start matching is the egalitarian one. So can you see that why the start one is the egalitarian one?
It's like it has to be at least 2n because all of them, if they have rank 1.
Yeah, the rank
But
one
then I'm
are,
not seeing how there is no matching with exactly 2n. Or
because if here everyone is getting the second rank, and here everyone is getting the first rank. So, but if anyone from men gets the first rank, then the corresponding women will get the nth rank. So reducing by 1 is increasing the women's side by n. So that's why there cannot be any more egalitarian any more matching which has the better egalitarian value. Okay.
Oh, I see. So, okay. So if any matching has even one difference in the men's rank, then the women's would go up by n. Okay. And then you would.
Yeah.
Okay.
I mean, if someone increases, then the women will go by n. Or if someone decreases, then that is even better. Like that, then it is decreasing in the both side. So yeah, there cannot be any more egalitarian value matching with more. So, and suppose there is another example. So let's look at this example. Okay, so here what is the minimum? I think we can do with the first one also only. And can you tell me what is the minimum regret value of this matching, of the underlined matching and the start matching?
Underlined is n.
Yeah.
And the start is 2.
Exactly. So in this way, basically you compute the regret value, and the goal is to basically find a matching that has the minimum regret. So here also you can see that the start matching is also the minimum regret matching. So it may not be true that the underlying matching is always, I mean, the egalitarian stable matching is equal to the minimum regret. It may not be true, but here we can see that it is, they are the equal, they are the same. Okay. So for this, so these two matching problems are like finding a matching that benefits both men and women. Okay. So we are going to see the third one. Okay. So the next one is called sex equals stable matching. So what we are going to do, this is a little bit different. So what we are going to do here is we compute a delta value for each matching that is basically is equal to so basically delta value is equal to, we take given a stable matching M, we take sum all the MR values of this of the edges that are in M, and then we sum all the MR values that are in W, and we subtract the first term from subtract the first term, second term from the first one, and of course here our goal is to minimize mod of delta M, because delta value can be positive or negative depending on which side has the larger value. So our goal is to basically minimize the absolute value of delta M. So here you can see that this sex equals stable matching, it is basically a global version of the minimum regret stable matching. So in the minimum regret stable matching, you want to minimize the maximum value of MR or WR, and here you want to, what you want to do, you want to minimize you want to take the sum of all the MR and sum of all the WR, and you want to subtract the sum of WR from the sum of MR, and you want to minimize that. So this is like a kind of a global version of the minimum regret stable matching. But the problem
Can
is,
we also say this is a relative version of the minimum egalitarian?
yeah, yes, I mean it's similar. I mean in the egalitarian we are taking a plus, and here we are taking a minus. We are subtracting them.
So it's like a relative, like the men and women are comparing. Yeah. Anyways.
Okay. So the problem, yeah, you can say that, I think. But the problem is that this problem is NP hard. It's NP hard to solve even if each men and each women have like a preference list of size 3. Then also the problem is NP hard. Okay. So this is the 3 stable matching matchings which are like doesn't benefit either men or women too much, and gives us a balanced stable matching. Okay, so Control D. So after we have done this, so you can just learn the definition of this stable matchings, and maybe during the presentation someone can paper presentation, one of you can present. I'll check the algorithms, and if the algorithms are not too hard, then someone can present the algorithm for one of the finding one of such stable matchings like minimum regret or egalitarian. Okay. Okay, so next we have, it's called stable matching with incomplete list. I think we have seen that the next topic. So I think we have already seen this topic, right? The stable matching problem with the incomplete list. So this is a problem where, so I'll tell you the definition today because we will not have much time, and we will discuss about this stable matching with incomplete list in the next class. So what is the definition? It can happen that in the previous cases we have seen that each man and each woman have a full preference list. They have a preference list over each man have a preference list over every woman every woman in the other side, and each woman have a preference list over every man. But it may not be possible always. That it may happen that for some M and W, M may want to be remain unmatched than to be matched with W, and similarly with W also it may happen that W may want to remain unmatched than to get matched with N. In that case, what we do is, in the preference list of N, we remove W from the preference list of so basically what we do, we remove the preference list of we remove W from the preference list of N, and in that way we basically get an incomplete preference list of N. So when we work with this incomplete list, then the problem is called a stable matching with problem with incomplete preference list. Okay. Is this clear? What is the stable matching problem with incomplete list? So it's, in short, it's called SMI. Is the generalization clear?
Yes.
Okay. So in the next class, we will see something interesting. That so one thing is that in a SMI problem, stable matching with incomplete list, the size of the stable matching may not be a perfect matching. The stable matching may not be a perfect matching. It may keep some men or some women unmatched in the solution. Okay. So one thing, one easy example can be like this. So M1 can have like W1 and M2 can have also W1. And suppose W1 have M1 after M2. And suppose, and in this particular example, we can see that M1 and W1 will remain matched, and W2 and M2 will be unmatched in the stable matching. So in this example, the stable matching is M1 and W1. So here we can see that M2 is unmatched. Okay. So similarly, we are going to, so in this way, we will prove that if some man or some women is unmatched in one stable matching in a, for a given instance here, that man will remain unmatched in every stable matching. So that we are going to prove in the next class for a stable matching with incomplete list. Okay. And the next thing is, and after that, we are going to see the problem, that is SMT, where the each man or each woman, not each, there exists some men or some women who has ties in their preference list. That we are going to do in the next class. So the stable matching with the incomplete list and the stable matching with ties. Okay.
So in this case, W2 is not on M2's list, which means M2 does not want to be matched with W2. And
Yeah.
so
So
we are not
maybe
including it.
suppose there is W2 and suppose there is M1 also here. Okay. So maybe let's do it this. So W2 doesn't want to be matched with M1, or M1 doesn't want to be matched with W2.
No, W2 wants to be matched with M1.
So W2, M2 and W2. So suppose W2 and M2 doesn't want to be get matched with each other. So now, but you can see that the current matching is a stable matching. You cannot change the matching to get
because because M1 W2 is
one.
not.
If you take any the other matching, then M1 W1 will basically block that matching. Okay.
Yeah.
So that is it. Okay.
And
so
if W2 had M2 on its list,
yeah, then it will be a old case, and it will be a complete stable matching, and M2 W2 will get matched with each other.
Oh, so even though M2 does not want to get matched to W2,
yeah,
W2 has M2 on its list instead of M1, then you should.
No, it cannot happen. Basically, we assume that if they prefer, I mean, if W2 is not present in the M2's list, then M2 is also not present in the W2's list. We assume.
Okay, I see. Okay.
Because that makes sense to give it. Otherwise, it will not be a matching. I mean, it will not. You will not be able to create a bipartite graph with that, with this instance.
Then it will become directed or something.
So yeah, so that's why, I mean, we assume that. Okay, so we'll stop here now. So I have some questions. So do you have to so do I need to do anything for so basically you want to credit the course, right?
Yes.
Yeah,
so
I want to.
I am creating this course.
Okay. So I'll stop the recording.